So as in last class we were discussing about beam element. Beam element. So this is two node element. Okay, two node beam element. So for example, we are having this is our beam element. This is having node one. So did you cover this beam element in your videos? Yes, no. Okay. So this is node one, this is node two, and this element is subjected to any type of loading like this. This is loading. Okay, so this is Qx. Okay, load per meter, Newton per meter. Then each node having 2 degree of freedom. So this node having this will be this B2. Then sorry, it is having only vertical and rotation degree of freedom. So this will be our P theta 2, and here V1 theta 1. So each node having 2 degree of freedom. Oh, that's fine. And this is having length L. This is having length L, and theta 1. Okay, so this is our x coordinate system. This is our y. Okay. So like initially we were discussing of some isoparametric that mapping. So what I'm going to do here, that I'm going to convert this beam, let's say s equal to 0 here and s equal to 1. Oh, so it will have how, so what will be s? S will be s equal to x minus s x1 by L, where x is the what x is the coordinate in x direction. So what we will get from here, for example, if I want to calculate at x equal to 1, so at x equal to 1, sorry, x at x equal to x1, what will be s? S will be 0. Then at x equal to x2, so this is our x1 at equal to x1, it is equal to x2. So what will be length will be x2 minus x1. Just I'm going to convert from one system to other system. Then at x equal to x2, what will be? S will be x2 minus x1 by L. This is, we already told that this is L only. So S will be 1. Okay. Then similarly, yes, similarly, what will be? ds equal to dx by L. So what we can say, dx equal to L into ds, like this. So I just converted from like x equal to x1 to x equal to 0 to 1 only. Here, uh, this one, this from x to s. This is not a issue, just I am converting. So now in terms of s, how we can write shape function and other thing. So in terms of in terms of s, element goes goes from 0 to 1. So in terms of s, all the element will be 0 to 1, 0 to 1, like that we have to decide. So what will be like, just I'm trying to do, I'm trying to get shape function for this new mapping system, this one, s equal to 0 to 1, this one. So are you getting something? Huh? Okay. So what will be the that trial function, because it is having 4 degree of freedom. So it is having 4 degree of freedom. So our trial function will be cubic. So B means like displacement vertical direction. B in terms of S equal to, it will be A naught plus A1x plus A2 x square plus A3 x cube. So this is in term of S. So in term of S, if I will say in term of x, what will be Bx equal to something A naught plus A1 x plus A2 x square plus A3 x, like this. Similarly, it will be in term of x. Okay. So what will your boundary condition? What will your boundary condition? So uh, here at x equal to 1 or x equal to, or like so. So this is our new element. This is our element x equal. This is s equal to 0 and s equal to 1. Node 1 having 2 degree of freedom. Theta 1, node 2, b2, theta 2. This is node 1. This is node 2. So boundary condition at x equal to 0, bs will be b1. Okay. Then at s equal to 1, bs will be b2. And at x equal to s, dv by ds will be theta 1, and that at x equal to 1, dv by ds will be theta 2. These are our 4 boundary conditions. So I will write like this. At x equal to 1, at x equal to 0, then at equal to 1. This will be your boundary condition. Okay. So first we have to put first boundary condition. So this one, 1, 2, 3, 4. This is separate. This is separate. So what first we have to calculate dB by ds. From this first boundary condition, from first boundary condition, what they are saying, at x equal to 0, b 0 equal to b1. So what we can say, from by using this boundary condition, what we can say, at x equal to 0, b1 will be e naught. Similarly, at x equal to 0, dv by ds will be theta 1, which means that we are going to differentiate, it will be a1 plus it will be A1 plus 2A2 plus 3A3S. So then it will be it will be overall A1 only. So then our what will we get? Theta 2 equal to, sorry, theta 1 equal to A1. Yes, I'm just going to put that. I'm just putting that those boundary condition. Yes, you can say yes or no. It's okay, then fine. Similarly, then second boundary condition. Second boundary condition. What is we having second boundary condition? At x equal to 1, b1 equal to beta 2 and theta 1 equal to theta 2. So what we will get from those boundary condition? B2 equal to B2 equal to A naught plus A1 plus A2 yes. So it will be A naught plus A1. It will be at 1. Sorry. B1 will be A naught plus A1 plus A2 plus A3 and theta at 1 equal to what we will get? We will get A1 plus A2 A2. So A1 plus 2A2 plus 3A3. Okay. So this one we are having B2 equal to A naught plus A1 plus A2 plus A3 and this is theta 2 A1 plus 2A2 plus 3A3. Now from here what we can say, from here add in place of A naught we can put B1. So it will become B2 equal to B1 plus, and in place of B1 we can put theta 1. Okay. I think we missed somewhere. Hmm. Sir, in theta 1 that's only the boundary condition one. Theta 1 equal to, no, no. There's something I missed there. L. So do we multiply by L here somewhere? Not theta 1. So wait. It will dx equal to L into ds. So, but we want to find dv. Wait. I will start again here. 1 minute. So, like this is our phase that trial function. It is a node plus a1s plus a2 square plus a3 s. What will be dv by dx? dv by dx will be, oh yes, dv by dx we are going to find dv by dx will be dv by ds into ds by dx. Now that's fine. So what is dv by ds? Something we did here. So what is yes? So from ds by ds, ds by dx, we can say 1 by L. ds by dx. Yes. So dx by dl, we have ds by dx equal to 1 by L. So in place of this, what we can put? and now it's okay. In place of dy, we can put this one. So dv by dx equal to dv by ds into 1 by x. Hmm. So we miss here boundary condition. So dv by dx actually what is theta is equal to dv by dx. I am to write here. So theta equal to dv by dx, not dv by ds, not dv by ds, because we are talking about this x coordinate. I think now we got. So we have to multiply here by l only. So this will be this dv by ds. So it will be theta 1 l, theta 2 l. Then this one also will be l, and then dv by what I did. Theta 2 equal to actually what will be by dv by dx. So this dv by dx equal to dv by ds. What we have to find dv by dx? ds a1 plus 2a2 plus 3a3. So a1 plus 2a2s plus 3a3s square into 1 by l. Okay. So at s equal to 1 is at x equal to 1. Array, I got somewhere confused. So can you help me? I got confused where I did wrong. This is correct. This is those these are correct only. So okay, this is correct. At x equal to 1, b equal to b1. So this is also okay. This is also okay. And this boundary condition theta 2 equal to a1 plus 2a2. Hello, can you hear me? So I just okay. Final answer I will write here. I missed somewhere. So what will be a final equal that a1 a2? So we will get a2 equal to, just check, a2 equal to should be minus 3b1 minus 2l theta 1 plus 3b2 minus l theta 2, and a3 will be 2b1 plus l theta 1 minus 2b2 plus l theta 2. So this will be our that a2 and a3. Okay, or a node and a node a1 we already calculated. So what is a node? A node is our b1 and a1 is our l theta 1. So all these all these value going to put, you said something, we will put in trial function. So what we will get? Overall, what we will get? Bs Bs equal to 1 minus 3s square plus 2s cube, then B1 plus SL minus 2s square L plus SQL into theta 1 plus 3s square minus 2s SQ into beta 2 plus minus LS square plus LSQ into theta 2. Yes. So now in terms of shape function, now in terms of shape functions, what will our displacement vertical direction will be Bs equal to n1. Okay, tell me how many shape function we will have here. We are having 4 degree of freedom. Hmm? I think right. Okay, so yes, 4 only. So n1, n3, and n4, these are four shape function. There's nodal displacement b1, theta 1, b2, theta 2. So this equation, uh, this equation we can write in this way, and then what will be n1, n2? What will be n1, n2? So n1 will be n1 equal to 1 minus 3s square plus 2s cube. N2 will be SL minus second term 2s square L plus SQL. Then N3 will be 3s square minus 2s cube. N4 will be minus LS square plus LS cube. Okay. So this one will be our N1 and this will be our N2. This is N3. This is N4. Okay. Then what is nodal displacement? What is nodal displacement? This is our nodal displacement. Nodal displacement. Okay. So what is N1, N2, N3? N1, N2, N3. This N1, N2, N3. These are the these are the beam ending shape function. Someone calling shape function, someone calling shear function also. So what is actually N1? N1 is the node 1 transfer. This it will represent the this N1 will represent uh, node 1 displacement vertical direction, and N2 represent node 1 rotation in this about z direction. Similarly, N3 and N4. So N1 and N3 represent the translation motion, N2 and N4 represent the rotation motion. So I will write here. So these two will represent translation motion, translation, and these two are for rotation. Hmm. Yes, I think you got some idea what I'm trying to say. So now we will solve one problem that it will be easy to understand. So, oh, you logged out. Okay, so we will solve one problem and it will be easy to understand what actually I am trying to say. So one thing I just want to mention here that stiffness for beam element, stiffness matrix, stiffness matrix for which this is our beam element, node 1, node 2. It is having 2 degree of freedom, V1, theta 2, V1, theta 1. So what will be stiffness matrix? It is having length L. This is length L. So K equal to E I by L cube, A by L cube. It will be 12 6L minus 12 6L, then 4L square 6L 2L square 12 minus 6L, then 4L square. I wrote only uh, one side element, and this will be symmetric. So it will be 4 cross 4 element. Yeah, 4 cross 4 matrix. For this type of element, this is two node beam element. This is two node beam element. Okay, or I will write full matrix also. This is symmetric matrix. So how we write? So it will be like this. So this will be 6L, and then okay, this will be minus 12. This will be 6L. Then this will be 4. Mhm. So 6L. Okay. Then 12. This is 12. This is 12 square and minus 6L. Okay. Then then we will solve one problem that will be easy. One more thing I just want to highlight here. So displacement at any point in the element. What will be range? 0 से लेके between 0 to 1. Okay. What will be our displacement? So this will be bs shape function. Shape function we already this equation we are going to use. This one only. This equation. So we have to use this equation Okay. So what will be our shape function? A displacement function that I will copy from here. This one. Copy. Okay. So I will write in terms of shape function. So n1, n2, n3, n4, then b1, theta 1, b2, theta 2. So this is our n1, n2, n3. Sorry, this is our n3, and this will be our n4. So in simple form, how we can write b equal to that displacement vertical direction. It will be 1 minus 3s square plus 2sq. Okay, then l s minus 2s square. Then I will write here 3s square minus 2s Then similarly I will take l common minus s square plus sq and multiply by nodal displacement b1 theta 1 b2 theta 2. So like this we can obtain. So do you have any doubt as of now? Okay. So then similarly bending movement at any point in the element. So bending movement bending movement at any point at any point in the element between 0 to 1. This is our range between 0 to 1. So what will be our bending moment? So m equal to ei, directly I am writing formula, you can drive if you want. Ei minus 6 plus 12s, then l minus 4 plus 6s, then 6 minus 12s, then l. This is in matrix form. Minus 2 plus 6s multiply by nodal displacement. So b1 theta 1, b2 theta 2. Okay. So one more, like we know that bending moment m equal to ei d2 by ds2. Similarly, then b will be ei d2. Then b what will b will be our that's displacement b equal to dm by dx. Okay, so it will be ei d3b by dx3. These are simple, like no strength of material things. I'm just going a little bit fast because it is not required. Oh, this is our that shear function, shear force. Not okay. Yes, shear force or something I missed. This is shear force, so I will. This is our displacement only. B. This is shear force. Shear force. So Now we are going to solve one problem, then it will be easy to understand. So you are also feeling what I'm telling you. So okay, one problem. This is problem. This is one of the beam. This problem you have to solve, and this is hinge at this location. क्या हो गई? Oh, sorry, I got disconnected. So this is one of the beam. I will write here. I will draw this beam again. So this is long beam, and this is hinge at this location. At this also, and this here having three location. Fourth one also. This is total four, and we are putting one load here. This is 8 kilonewton. What the dimension? So this is 400 mm. This is also 400 mm. This is 400 mm. So all element having same dimension. So how many node we are having? Node 1, 3, 4. Okay. Yes. So node we are node what we have to calculate, and what is the other parameter. So E equal to 200 gigapascal, and I for this beam element given 10 to the power 5 mm power 4. Okay. Okay, fine. So we have to find deflection, find deflection and shear in a continuous beam shown in the above figure. Okay, so we have to find that displacement shear force in a beam. Okay, so this question we are going to solve. So now first we have to find how many node we are having. So this is our node 1, node 2. This is also one node. So node 3. This is node 4 and node 5. Total we are having 5 node, and each node having 2 degree of freedom. So this is beta 1, theta 1, b2, theta 2. This is having b3 and theta 3. Then b4, theta 4, b5, theta 5. So total 5 degree freedom. Okay. So from this figure we can see that this is symmetric about this load. This is symmetric about this loading condition. So what we can use, we can use this symmetric condition, and we will we will find that this part displacement and that rotation, and this will be same for this right side also, because this is symmetric. So left side we are going to consider. So now we are going to find solution of this problem. How we are going to solve? Just see. Let's see. Then using solution, using symmetry, only half of the beam, can be modeled. How? This is our beam, and this is hinged at this location, and what we can, we will put ruler here, because it is allowed to move in vertical direction, but it is having also zero rotation. So this is our 400 kilonewton force, 4 kilonewton force, because it's a total 8, so it will be 4, 4, 4 both side. Then this is having length 400 mm. This is having length 200 mm. Okay. So now what will be our degree of freedom? How we are going to define? So node, how many node we are having now? 3 node. B1, theta 1, B2, theta 2, B3, theta 3. So total 3 node. Okay, fine. So now what we have to do, we have to find that stiffness matrix for each element. So like this is our first element, this is our second element. So element 1, this is element 2. So both element we have to find the stiffness matrix. Okay, so we will start with first element. First element, what will be first element? As we discussed that for any element, what will be stiffness matrix? This will be our stiffness matrix. This will be our stiffness. Just we have to put value of length and other parameter. So for any element, this will be our stiffness matrix. Okay. So I will just remove this one. Here, given that E equal to 200 gigapascal, L equal to 400 mm, E equal to 10 to power 5 mm power 4. Okay. So what will be in terms of kilonewtons? It will be 200 kilonewton mm per square, mm square. Yes, fine. So now by putting these all value in this stiffness, so for first element, first, but stiffness will be K1. So K1, okay. Similarly for second element, similarly, similarly for second element, but only second element we have to take care. The length will be 200 mm because this is our second element. So only length will change, on remain will be, or other thing will be same. Okay. So now we know that for first element we are going to write that equation, force equation. So how we are going to write for first element? So I think I got disconnected. So this problem we are going to solve. Just I am starting this problem. This is one of the beam element. This is one of the beam element. It is having total 1, 2, 3, 4. Total 4 node, and each node having 2 degree freedom, theta 1, that vertical and rotation. So this node having 2 degree freedom. Similarly, this one, this one, this one. And this is from by looking this problem, we can see that we can easily see that this is symmetric about this line. So just we have to model only right left side, and similarly will be that right side will be same. So but we are using this symmetric